Okay, so what we're going to do now is effectively level up so that we're like kind of actually using Haskell now. The functor, applicative, and monad are going to be the final three things that we need to like sort of be fully engaging with functional programming. So I'm keen. It's going to be like a theoretical lecture. I don't have an expectation that everyone's going to understand everything that I say today. So don't get stressed out if you don't understand everything. That being said, we should be able to absorb a lot of it, but it is going to take a little bit of reflection. And I think there's like exactly one functor-based question on your assessment, which is not due this Friday, but the Friday after. And then I've already written an EdSTEM announcement with some hints for A1 programming, if you guys. So how's that one going? Yeah, it's like we actually sort of start like so. Let's start it earlier than last time because let's remember that things that sort of look easy may actually sort of not be that easy when you switch paradigms. One of the hints is just this cryptic drawing of how you may actually want to rotate a triangle without actually rotating it. So if you just sort of stare at this picture for a bit, which I'll release on Friday, this is going to how to tell you how to rotate a triangle. You have the same drawing. Yeah. Good, good, right? This is the drawing that you need. It's just about realizing, oh, that's if you just take the first thing of the first row and like the next two things of each, like you can realize that you don't actually have to rotate something. You can actually do it kind of iteratively if you want. So take a look at this, but I'll also post a bunch of hints on Friday. I was going to post them now, but I thought, no, you need to suffer a bit, right? So suffer a bit, and then on Friday I'll give everyone some push as well, so everyone can feel a great sense of satisfaction when either they're given the hints or solve them themselves. Okay, so functors and applicatives are what we're going to be doing today. So a couple weeks ago, we were talking about higher order functions, and one of the higher order functions that we discussed was the map operator. That is, if I gave you a list with something with A in it, and I gave you a function that took A to B, then you could get back a list with something in B in it. We call this a structure preserving operation because there is no map that you can do that's going to change like the length of the list, right? You're always going to get something back that's the same shape. And what we want to do today is actually generalize this notion to all things that have structure, right? Because anything in Haskell that can be put in a box is considered to have structure. So like maybe has structure, either has structure. The trees that we built have structure, and thereby all of those things should also be mappable. Okay, so again, functors are the generalization of map, right? If I wanted to summarize today's lecture in one sentence, that would be the sentence. Okay. So what are some other structure preserving operations that we could sort of consider? I'm said, okay, so we have map, and map is specifically for mapping functions over lists, but there's actually something in Haskell called fmap, which is the mapping operator for anything with structure. And if we look at what its type is, let's see, what's the type of fmap? You're going to see something like this. It's going to say, okay, give me anything that's a functor and a function that goes from A to B. And that structure over and with something with structure over A, and I'll give you something back with structure over B, where this structure has to be a functor type of structure. We're going to flesh that all out. All right, so we know that we can map over lists, so it should be no surprise that lists are functors. So if I call the fmap operator over, oh, so this isn't a list, this is maybe. Okay, so let me just finish what I was saying there. We had map. I could map plus one over one, two, three, but I can also fmap plus one over one, two, three, right? These are the identical operations. All right. So something else that we have with structure is maybe, right? So this is the sort of basic error signal type. So if you have maybe A, you get the extra data, nothing, and then everything with A with a jest over it. So maybe ints would be like just one, just two, and the error handling would be nothing. Okay, so I'm saying maybe, or sort of jest is like structure that we can consider. And when I map, it's sort of like going inside the structure and making changes inside the structure. So it's kind of like if you have a box and I let you go into that box and make changes inside that box, can you change the box itself if you're inside the box? No, right? So that's like how I like thinking about functors. It's a type of operation that lets you go inside the box, right? And join the box party. Okay. So if I told you that we have an fmap operation, we're given a function a to b, and given a maybe a returns to a maybe b, it should be no surprise that it does this, right? I can say map greater than 0 to just 1, and it's going to give me back just 2, right? Because this greater than 0 was permitted to go inside the just box and apply greater than 0 to 1 to get true, and then it left. Does this change the structure of this maybe type at all? No, like we still have one jest, we apply a map, we still get it one jest. What do you think should happen here if we f map greater than 0 over nothing? Yeah, we should get nothing back. Does that sort of make sense? Like what did we map f to the empty list? If I said map +1 to the empty list, what are you going to get back? The empty list, right? So in both cases, that was sort of like the degenerate case. Like nothing was sort of like the degenerate maybe case. Empty is like sort of the degenerate list case. So it should be no surprise that the map is just going to effectively make no changes if you give it sort of like the empty box or the degenerate case, right? This is a more interesting one. What do you think? What other boxes do we have? So I said maybe, we said either. Like how else can we collect things together? I'll just drink coffee and let everyone stew in discomfort. Yes, but that's maybe a little bit too comp. We have like a much simpler box than that. Yeah. Yeah, go ahead. Yeah. Yeah, we have lists. Do we have a set container? I don't think we talked about tuple. Okay, so do you think we should be able to map over tuples? Like so like if I have a tuple of length 3 and I map over that tuple of length 3, I should get a tuple of length 3. Okay, do tuples have to have the same type inside of them? Okay, so this is a little bit. Okay, so what should happen here if I sort of say let's f map the +1 operator to 0, 0? What is going to happen? This is a little bit tricky, right? Because the f map, we're going to give it a function that goes from A to B. So like which one, if tuples are like A, B, all right, so let's consider this. I want to give a function A to B, and I want to be given a tuple, and I want to get another tuple back. But these tuples don't have to have the same position in them like this. They can be like C, D. So the question is, well, where's the A in this tuple, right? Because A has to change to B. So this is a tad tricky. But remember currying. So what is the structure of a tuple? So this is interesting. Okay, so let's go. I'm going to press enter here. And we're going to see that's 0, 1, the second position, not the first position. But remember currying, right? So what does this do? What's going to be the result if I hit enter here? 1, 2, because what is this? Yeah, this is a function that takes B, and it puts B in the second position, right? Okay, so if I have a tuple like this, and I'm going to say CA, we're going to get back CB. And that may seem strange, but how's another way of rewriting this tuple constructor? Well, I can rewrite it like this, can't I? Because of currying. And therefore, this is the structure that's invariant, right? So I can say maybe where F is that. And if I put that here, is it sort of more apparent what's happening? All right, so the container effectively is like just the last position in the container is all the previous positions where the thing that you get to put in is the last position. Yeah. What do you think will happen if I do it with a triplet? Why do you think that? Last position. Yeah, because with a triplet, you would have something like A, B, C, D, C, something like that. Like this. And let's test this out. If I F map +1 to 0, 0, 0, unless I look like a fool, it changes the last one. Okay, so that's how the functor will work over lists, right? So that was a pretty interesting one. What other structures do we have? Maybe like I make like a tree, right? And so this is like we don't necessarily get constrained to like only mapping over data that's like lives in the prelude, right? So here's our custom data type for a tree. I think we played with that a little bit last week when we made that an instance of foldable by defining a fold operation over that. But does it make sense that if like I give you a tree with a bunch of nodes, that I can like make changes to like what the values inside the node are without actually changing what like the structure of the tree looks like? All right, so we can have a function over a functor over a tree. Like suppose I have a tree, it has two leaves and a node. So the leaves have one, the node has two, the leaf has three. I may just want to say, okay, increase all of the values in the nodes by one, and by that I can just say, okay, f map +1 over that tree structure. Let's consider what the common pattern is here. Okay, so I said I have f map. I can map a function a to b, and we go from maybe a to maybe b. I have f map. You give me a function from a to b. I go from tree a to tree b. I have f map. I go from b to c. And this is the tricky one where I go from like tuples with a in their first position, with a b in their second position, to tuples with an a in their first position, to a c in their second position, which we can write like this. Is it any surprise that we can do the same thing with either? But either has two positions, right? Isn't this confusing? Well, it works the same way that the tuple one works, right? We can partially evaluate either A and then give it one extra type. We talked about this last week with higher kind of types, right? So either can take a concrete type and be in waiting for another concrete type. Does it make sense that we want the second position here to be changing rather than the first? What are we putting in the first position in an either? The error type. What should we map the error type to? Itself. It's effectively the same thing as the empty set or nothing in a map, right? So if I do something like, okay, let's f map +1 to left error. Whoops, I need some brackets. Right, that's working as intended. You want error signals to be passed through. On the other hand, if I said f map +1 to right 1, there's your structure preserving operation, right? So that's working as intended. So for either, that I write, yeah, that's the structure here that's remaining invariant is either the error type, right? So you can still have functors over data types which expect multiple concrete types to come in. You're just changing sort of the last one that goes in. Okay, so the master pattern here is effectively give me a function a to b. Give me something with structure over A, and I will give you something back with structure over B, right? That's going to be the typing information. You think this is going to be sufficient if I define is it possible to define a mapping operation on lists that types like this, that does something dumb, that like does change the structure? Okay, so can I define a mapping operation that like this? Okay, so I can say there's f map. This is f map for lists. Right. And I said that the important thing is that it has to be structure preserving. Will this work? Is it structure preserving? Does it change the length of, if I give it a list of length 3 and the +1 operator, does the structure change? Yeah, everything becomes 0, right? Okay, so how do we then reconcile that? I'm saying like a functor needs to be structure preserving. How do we reconcile that within the system? Not only do we have to define structures that define, okay, so remember these classes, and these classes are sort of collections of types. And in order to belong to a class, you have to define a bunch of functionality, right? So in order to belong to the foldable class, you have to define a fold. In order to belong to the class of functors, you need to define this f map operation, right? So that is to say, you need to give me a mapping operation, but in addition, these mapping operations are going to have to satisfy some rules, like the structure has to remain invariant if you do a map. And so that's the first thing we need to know, right? This is how you become a functor class, by defining this function, right? But in addition to defining that function, you have to satisfy rules. And these rules aren't going to be enforced by Haskell, right? Haskell just expects that you've sort of verified that your functor is satisfying these rules. The first rule here basically is the thing that says you have to be structure preserving. If you map the identity operator over your structure, you should get the exact same structure back. Does that sort of make sense how that first rule is going to check that like the box shape hasn't changed, right? It's like if I'm saying you map this function, you should get the exact, if you map the identity function to your structure, you should get the exact same thing back, right? That none of your structure could have changed. The second rule here is just a statement about how function composition distributes over the mapping operation. And that says, if you map G composed with H, that's the same thing as mapping G and then composing that with mapping H, right? Okay, so not only do we have to define this mapping operation, we also then have to go and prove that these rules hold. How do you suppose that we prove these rules hold? Or like, what do you think the sequence, if you're Haskell programming, what do you think you end up doing? Like, what's one practical thing that we learned about last week that could be useful in this setting for check? Yeah. Remember quick checks? Quick checks were exactly the things that tested properties. Quick check was effectively invented because we need to ensure that our functors and applicatives satisfy properties, right? So doing a quick check is going to give you a quick and dirty confirmation that your functor probably isn't broken. So if we run a quick check and it says you're fine, do we conclude that we have a functor? No. Okay. But do we have some evidence that it's probably a functor? Okay, what do we really need to do in order to prove that our functors are functors? We're in a rewrite system, right? What do? We write a proof. We do math. We rewrite it to demonstrate that these things actually hold. Okay, so here's an example of the list functor. That's the one that we used last week, right? I'm just saying if you map anything to the empty list, you get empty list back. If you map f to x cons x's, you get f of x cons f map f cons x's. Okay, so let's investigate how we can actually prove that the functor rules hold for this list functor. I'm just going to show you some usages, right? So I can map +1 over 1, 2, 3, get 2, 3, 4. Structure hasn't changed. I can f map greater than 1 just to show you that like A and B here can actually be different and you're going to get false, true, true. But in either case, the box hasn't changed its shape. The structure has remained invariant. You should know that we also have an infix operator for doing f maps, which is actually my preference. Which actually kind of makes sense here, right? So if I had a function like +1, what does it mean to say this? This sort of like the $ symbol we said was apply, right? So this is like saying, oh, apply the input 2 to f to get 3. Why do you think this sort of makes sense then? I'm saying apply the function f to every member inside of this box, right? So in both cases, you're sort of doing function application. It's just that this function application is kind of fancier because it gets to sort of go into the box. But in both cases, function application is what we're doing, right? So that's why we've utilized this notation. Okay, so I prefer using this $sign operator. You may have encountered it when looking at Haskell code online because this is very common. So we can use the infix operator and I can say +1, map that over 1, 2, 3 to get 2, 3, 4. Greater than 1, map that 1, 2, 3 to get false, false, true. Okay. And then we can I sort of jump between using the prefix or infix notation in my proofs, depending on however it makes it look easier. It's sort of I find it easier to sort of pull out the patterns using the infix notation, but I'm going to do both today. And you just pick whatever flavor that resonates better with you. We're certainly not going to privilege one over the other in marking. Okay, let's maybe write the maybe functor. I can't actually run them because we can't overload what's in the system. But remember, we have sort of data for maybe A, which is nothing of nothing or just of A. And if I want to write an uh, instance functor for maybe where, so what do I have to define here? I have to define an fmap operator, which takes A to B. And then I have to go maybe A to maybe B. So what do you think fmap of F over nothing should be? Yeah, nothing. Is there like anything else that we could have put here? No. So one of the problems with this course is that there's not actually very many functors or applicatives that exist that satisfy the laws. On the list type, for example, there's exactly two applicatives that exist on the list type. So it's tough to ask questions, but you should remember when programming, sometimes there's no choices to be made. There's no programming per se. You're just sort of trying to type properly. Okay. What about this one? If I fmap f, a function that goes from A to B, over just A, what goes on the right? So now there's like more options here. Should I put nothing here? Yeah, just B. Well, just B. I don't have a B yet. How do I get a B? I have an A and I have a function that takes A to B. Just fab. I love it. That's what I'm going to call it from now on. It's fabulous. All right. So just fab B, right? So less fabulous. Okay, fab A. Okay, so here you go. Here's the functor type. And it's very sort of intuitively clear that this is never going to be able to change the structure. Because if you give me one just, you're just going to get one just back. And if you give me nothing, you get nothing back. Okay, so there's the maybe functor. And you can see that I can say +1, map that to just 1. Whoops, I think I need some bracket. Oh, just 1, map that to just 1 to get just 2. Or +1, map that to nothing to get nothing back. Okay? Okay, so now let's go ahead and prove that one of our functors actually satisfies these functor rules. I wrote a little supplementary here. So you can pull that up on your laptops if you want. It's just going to enumerate, it's just going to put there, because I'm going to have to keep jumping back and forth to the definitions. So I'm going to keep jumping back between this set of slides and the definition so we can back reference, but also you can have it in front of you if you want. Okay, so some things that we're going to have to reconcile with is the point free form. So remember, if you have f equals g, that's the same thing as saying f of x is equal to g of x, right? So these rules will actually still hold if you put an x on both sides here. But maybe this is something that's a little bit hard to grapple with, but you'll get used to it, is this notion of applying and unapplying, which we're going to talk about. I thought it was there actually, but okay. So some of these proofs are going to be more straightforward than others, right? Because we have to prove these work on a variety of data, and some of that data is infinite. It's like I wouldn't say maybe is infinite. It's like infinite because it's a product type, but there's two cases, nothing and just. And if we cover those two cases, that should be okay. But things for like lists, that's a little bit more complicated because there are an infinite number of lists of different structure, right? The list of length 0, the list of length 1, the list of length 2, and so on and so forth. So we're going to have to use induction to prove some of these things. But we're going to have to use sort of a different style of induction than we have been using. So the induction that you've been using now is basically an induction on the natural numbers. What we have to use here is something called structural induction. The idea is very similar. It's just that we have to change our language a little bit, right? So the statement of structural induction is such, right? If you have S, and S is some recursively defined data structure, like list of A or tree of A, that has substructure. So the substructure of a list is its tail or sublist. The substructure of a tree are its subtrees. And there is some well-founded partial order, which means that, so well-founded means your order has to terminate. There has to be something the smallest. You can't have an infinitely descending order. So the naturals has this property. You hit 0, that's the smallest things, but the integers don't because you can count to negative infinity. Partial order means that two elements are either, if you have element A and B, A is either greater than B less than B, or equivalent to B. And this is a little bit different. So if you have two lists, is there a way to order lists? What's one way of ordering lists? Should like the list 1, 2 be bigger or smaller than the list 1, 2, 3? Yeah, it should be smaller, but how did you like smaller by what measurement? Length. Okay. But so is the list 1, 2 less than or greater than the list 3, 4? Well, they're the same, right? Because they have the same length, right? So this is what a partial order is. Partial order means a lot of things can have the same order, but I don't care to sort of distinguish between list of length 2 from other lists of length 2. I just care to distinguish that lists of length 2 are smaller than lists of length 3, right? So a partial order is sort of weaker than a total order. A total order would insist that any two elements that aren't equal, one of them has to be larger than the other one. A partial order means, no, it's okay. Like a bunch of things can be ordered the same that aren't identical. So like how could we order trees, for example? That's a little bit less obvious. Right? We could still do the same thing, maybe like by counting the number of nodes in there. But the important thing is we have some measurement on the data structure that's getting smaller, right? In terms of this recursion. Okay, and you're never going to have to set up the well-founded partial order. It's usually induced by how we're writing down the recursive data structure in the first place. Okay, so structural induction implies that if you have some predicate P, which is true for all of the minimum structures. So the minimum structure of a list is like the empty list. The minimum structure of maybe just a and nothing. So like the small, like maybe a tree, the smallest tree is one that's like a single leaf, right? So if it's true for all minimum structures, and if you consider X and the statement is true for all immediate substructures of X, if you can prove that PX is true as well, then it's true for everywhere. Okay, so it's kind of like we have a statement about truth about lists, and we've shown that truth statement is true for the empty list. We consider a list X con X's. We assume that it's true for X's, that's tail, and show that it's true for X con X's, then it's true for all lists. It's very similar to induction. It just has it's a little bit spicier, right? That we can sort of now do this over recursive data types. So we're going to do this. So it'll become more clear in its usage. Okay. So this is the easy one. Effectively show that if you map the identity operator over a list, that you get the list back. So I'm going to leave you, maybe we'll do this for homework, or maybe we'll do this in one of your tutorials. What I want to do now is prove that the list functor satisfies the second functor rule, right? So maybe either write this down somewhere or like open up the supplementary slides. I want to prove that G composed with H, if I map that to X's, that's the same thing that if you do G map and compose that with H map X's, that you're going to get the identical thing back. Okay, so here's how we start with assumptions and definitions, right? So when you're doing these proofs on your homework, so now I have to demand that you're very like nothing should appear out of nowhere. I'm going to demand that every single line that you write is justified by like line number, right? Because we're just rewriting Haskell lines now, right? So everything should be producible by referring to some Haskell line or referring to your proof itself. And I'm not doing this to be cruel. This is going to help you not make mistakes. Okay, so let's check out what we're going to be able. I'm going to give you a bunch of things that you're allowed to assume. Okay, so when doing this proof, the only things that we're allowed to utilize are these two rules of the list functor. I know that anything maps to the empty list gives you empty list, and I know that F maps to X cons X gives you F applied to X cons F map to X of X's. That's the two things that define the list functor. We shouldn't have to utilize anything else when showing list functor has the type of property. Okay, you can take these for granted. I can't really prove them, so you can just refer to them as the composition rules. And I'm just going to say all of these things that I wrote here can be deemed equivalent, right? So if you have F composed with G and you give that X, that's the same thing of F composed with G $X. That's the same thing as F $G of X, which is the same thing as F $G $of X. It's just showing you that you can change the order of sort of evaluation in a composition, whatever way that you please, right? So feel free to say, I did this by composition rules. And I didn't write all of them because you can always replace dollar signs with round braces if you want, where we're equivalent, because it's the exact same. They're just basically notations for one another. This is sort of a little bit harder to grapple with, but it's effectively a statement about which way down your expression because we can say A is equal to B is equal to C is equal to D. But you can also say D is equal to C is equal to B is equal to A. Equal means equal, right? That means you can move up or down an expression. So to apply and unapply, like apply basically means you're moving down the expression and unapply means you're moving up. So because this is kind of weird, I will write this. I will get rid of this. Okay. So suppose you have a function that's like +1 operator. And I'm like working out things here. I'm like, okay, I have f of 3 and I get from f of 3 4. Okay, that's not too complicated, right? So I'm saying, okay, so I've applied 3 to f to get 4. That is to say 4 is deducible from f of 3. What else can be deduced from 4? F of 3 can be deduced from 4. That's called unapplying f, right? So when you apply a function, that's going from here to 4, right? To deduce 4 from +1, 3 is to apply +1 to 3. To deduce +1, 3 from 4 is to unapply f. Was this the only? So what's the problem here? What other things can I unapply? What other things can I deduce from 4 that I could have written at this equal? Yeah. Huh? Yeah, 4 could have been the application of 2 to +2. Like 4 could have been got by taking 5 minus and then giving that 1. 4 could have been deduced by sort of dividing 8 by 2. Right? So like there's an infinite number of stuff that you can unapply to get 4. You're usually doing so with purpose. But if you're confused by this, if you unapply f to get something, that just means that if you should be able to apply in the opposite direction, right? If I'm saying 4 was deducible by unapplying this, then if I do this, I should get back 4, right? Okay, so that's what this statement means, right? Suppose I have this function +1, that's f. To deduce 3 from f of 2 is to apply f to 2. And to deduce f of 2 from 3 is to unapply f, right? Because we need to move from this side of the equation to that, but importantly, from this side of the equation back to there. Okay, so when you see apply and unapply appear in my proof language, that's what I mean. Another thing I want you to do in your proofs is not this. Okay, so you're going to see my proofs and things will seem kind of magical, but in truth, this is sort of how my proofs work. I go, okay, A is equal to B is equal to C, and I'm going to leave that. And maybe I had E and this was equal to D and this was equal to C. And I'm like, aha, okay, so I have like a common point. Okay, so I don't want you to say A is equal to B is equal to C and E is equal to D is equal to C. Therefore, E is equal to A. I want you to this is like your rough work. And then the proof has to be presented like this. Like that. Because like this is better. You're just following one line of reasoning and concluding A is equal to E. But I don't want to give you the impression when I give you my proofs today that that's how I did them. I did them by working like from the bottom and from the top and finding some common point and then switching one of the sides. And so the benefit is when you're working when you do this, these will all be applications. The easy one. And then you flip one of them and you just change all applications to unapplies, right? Because we knew like, oh, we can unapply an infinite amount of functions. Which one do I unapply? How do I even pick? So that's sort of the strategy at play here. Okay, so let's actually do one. Okay, so I want to prove the functor law on lists. So here's the functor law, right? G composed with H mapped to X's, a list, should be equal to G mapping, compose that with H mapping to the list. So the first thing that we do in our proofs always is state the thing that we're trying to prove. And we can use mixed Haskell in English in this setting. So I'm saying for any x's which has the type list of A, I am asserting that P of this list is the truth assertion the second functor law holds for that list. Everyone with me? Okay, you stop me if anything does not make sense. What's the first thing that we have to prove in this? Same as the regular induction. We always have to prove the base case, right? So the base case here is what? What is the minimum structure on X's? Empty list. Okay, so I have to prove that this works on the minimum structure for this data type. We're lucky here because there's exactly one. It's not always going to be the case that there's exactly one minimum structure. Well, I'll do one of those later. Okay, so let's see if we can prove that this statement holds for the empty list. What will this rewrite to? We have a limited set of rules that we can work from. There they are. Right, so I'm saying, what does it mean to map something to the empty list? Is there a rule here about mapping something to the empty list? Has to be empty. Okay, so if I map that to the empty list, I'm going to get empty list back. And we get that by applying the rule g.h functor, right? That's sort of line 2 down there. What do I do from here? I have to make this turn into this. But that's just the empty list. How do I start materializing functions now? Unapplying stuff. What should I unapply? G. Okay, so I need everyone to be with me because if not, then we have to talk about this a lot. I'm going to say the empty list. If I map G to the empty list, what do I get? Empty list, right? So therefore I can say, from this empty list, I'm going to unapply Gmap. So if this confuses you, just move in the other direction. If I take this, if I map G to the empty list, do I get that empty list? Yeah. So if I can always go back up, it's true, right? So if I reverse the direction, then instead of saying apply, I say unapply. Okay, so now we've materialized G back in. How do I get back the H? Do we still have an empty list? Can I unapply H from that empty list? Let's do it. Okay, so I unapplied H again from the empty list. Now we have H back. Okay, so now we seem to have all of the pieces, but I have to have a composition there. Is there any way for me to get the composition operator into there? I said, look, all of these things are equivalent. So by composition rules, I just put a dot there. Have we established that the second functor law for the base case? Okay, that was the easy one. All right, let's move on. Okay, so therefore it's true at the base case. Let's do the induction now. So what are the core pieces of doing an induction? What do we do in the induction step? What's the first thing that we have to do? We sort of have to assume something, right? Okay, so I'm saying here's my induction hypothesis. I need to prove that the second functor law works at x cons x's. Under the induction hypothesis, that it's going to work at all of x con x's substructure. And in this case, the substructure is just x's, its tail. So I'm saying assume P of the tail and consider P x con its tail. So we're assume P x's and consider P x con x's. Okay, so I now have to establish that the second functor law holds for x con x's, presuming that we already know that this is true. And what does it mean that this is true? It means that we can utilize this expression as if it's already been proved. Okay, so let's now do here. What's the only thing effectively that we can do at this stage? Again, you don't have to think too much because there's limited, we only have the definition of the functor, right? So we have a function, we're mapping that to this. So what do you think we should utilize? Yeah. Yeah, there's two rules that we had. Should we use this one, the empty list one? No, should we use this one, the one on, okay, yeah, so you don't have to think too hard. You just have to be very detail-oriented with this. Okay, so what does it mean to map g.h to this? Well, it means to take g.h and apply it to the head and then to connect with the mapping to the tail. So that's that, right? Take G.H and apply it to the head, and then connect G.H to the mapping of the tail. Cool. What should we do now? So what is one way to know that you've done your induction wrong? It's a good hint. You don't use your induction hypothesis. If you don't use your induction hypothesis in your induction, why are you using an induction? Is there any way for us to exploit our induction hypothesis? Do you see this anywhere? Yeah, it's this, isn't it? Okay, so let's use our induction hypothesis. What does that mean? It means, oh, I can replace this expression with this expression. Agree? Okay, so I'm going to replace that expression with that expression by our induction hypothesis. Okay, so what should we do next? We're trying to reorder this to get the right-hand side here. So now we want to start doing some unapplies. And these may be a little bit trickier. Do I have the colors? No, not. Okay, I'll rearrange some stuff and then maybe it will become more clear. Okay, so I'm going to get rid of that composition operator by like using my composition rules to put dollar signs in. Do I have colors yet? Okay. Do you see anything here that I can pull out? The objective is always to like sort of apply and unapply stuff. Is there anything here do you think we can unapply? Okay, maybe I'll highlight some stuff. So I'm taking G and I'm applying it to some scalar. And I'm taking G and then I'm mapping it to some list. What is that? Yeah? We pull G out. Aren't we mapping G over something? We are mapping G over this. Right? Right? If you just see this as sort of Y and then see this as Y's, then it becomes clear that you're mapping G over Y. But in this case, Y's is H mapped over X's. Do you see it again? So what is that in there? What can we pull out? We can pull out the H map, right? And we did that by unapplying G map and unapplying H map. If I then use the composition rules, what have I rewritten to? That's the right-hand side. So what can we conclude? P x con x's. Does thereby Haskell's list satisfy the second functor rule? For sure. Yes. Okay, which is different than doing a quick check. Okay, and this is the power of, remember, functional purity, remember referential transparency. That's the thing enabling us to make these rewrites and saying this is the same, like our Haskell code satisfies these rewrites. It's obligated to. The paradigm insists that we're able to make these rewrites because doing this can't change some global variable which screws everything else up. So we're seeing why referential transparency and what's the purity exist. If I were to put on your exam, now that your exam is written, I'm just going to start like dropping hints about questions that are on your exam through. Oh, and the other deal is, okay, so there's a Bear team in the NHL playoffs. The Boston Bruins are Bears. So for every round of the playoffs they advance, I will tell you one of the short answer questions on your exam. They're not going to make it very far, right? So I've always told my class if my hockey team wins the Stanley Cup that everyone gets a 7, but they're cursed, right? So that was never going to happen. They haven't won since 1967, which is like one of the longest running droughts in sports history. Okay, so if I were to say like what is referential transparency or what does it mean to be functionally pure? You just say, oh, equal means equal. Like I can rewrite expressions without changing program behavior. Okay, so that may be. Oh, and I think certainly it is the case that your 10-mark question on your exam is like prove that this is a functor, like one of the laws. So something like this. So do practice doing this. Oh, and the other thing is to punish people who are going to take the deferred, who don't have a genuine reason to take it. These don't necessarily apply to the deferred examination. Years ago, there was a rumor that propagated that the deferred examination is easier. I have no idea why that's the case. Like the numbers aggressively suggest that isn't the case. Okay, so enough talking about the dirty exam. All right. Therefore, we know that equation one follows from the principle of structural induction, and thereby we have proven that this data type for lists satisfies the laws for being a functor. Okay, suppose we want to do it again, right? So here's a tree structure, and I want to be able to say, hey, like take greater than 2 and map it to this tree. Let's go ahead and write the functor for this, and then I'll quickly go through how a proof for that one will look because it has a little bit of a nuance. Okay, so if I have data tree A, do we have leaves? No. Okay, so this is sort of like, okay, I want to do it a little bit different here because I could have an empty tree, but I'm going to say the smallest tree is actually just a single leaf, and otherwise a tree is a node with a tree to its left and a tree to its right. Does that make sense? Okay, so we cannot have an empty tree. Now I want to do something like I want a instance for functor of tree where, and then we have to define an fmap operator, which given A to B and a tree of A gives me back tree of B. Right? And you see, like, what's the invariant structure here? Well, it's the tree container. Right? We shouldn't start materializing new nodes or like, switch the left tree from the right tree or anything like that. Do not define this in Haskell. Don't do this. Haskell gets cranky, or at least it used to. It wants to be able to infer the types using its type inference engine, but nonetheless, it's still good practice to include this as a comment. Right? Haskell programmers will do this. Okay. So we want to write a mapping operation on this data. Something I told you ages ago is that in order to define a function on custom data, really all you need to do is make sure that there's one definition for each thing in the data. How many things do we have in our data here? 2. Okay, so we need a minimum 2 fmap operations. So fmap on with f for leaf of A. We'll put back in our fab function. Fmap fabulous. We is something that's tree, a node, tree left, then A, then tree right. Okay, so this one's the simpler one. What does it mean to map to a leaf of A? We get leaf, fab of A to get B. All right, what about this one? All right, so it's a node. It's 3 things here. This needs to be B. How can we get a B there? FA, yeah, fabulous of A. But what do I put in here? Yeah. Recursion. Okay, so we take this and we map over the left tree. And we take this and we map over the right tree. It's okay to use this infix operator when defining the prefix operator, but you can't do the reverse. Haskell insists that you're defining fmap. Right, so that is to say, practically speaking, when you're defining an instance of a functor, these can only appear on the right-hand side of equals. Okay, you think this is going to work? Was there anything else that would have typed here? Like, I guess I could have like switched this left to right and right to left, but would that work? It would immediately fail the first functor law, right? We couldn't map identity to this. Suddenly the tree has been mirrored, right? So exactly one sort of, there's many functors that would have typed properly, but there's only one functor that is considered lawful, right? That's the terminology here. Yeah, I know there's a meme, like, so someone please create that meme, the lawful good, lawful neutral. Maybe put a bunch of applicatives and functors in there. I'd like to see that. Okay, so I'm saying that this should already work, right? So I can have a tree, which is a node, which is a leaf 1 with lead. Leaf 1, which will never happen. Leaf 3, and we'll see if this works. Okay, so I have a tree, which I can't look at because I didn't derive show. So let's do that. There's my tree. Let's map greater than 0 to this tree. There you go. It's our functor working. Okay. So do we have a functor? I don't know. Probably. So how can we like affirm better our probably stance on this tree? Well, the first thing we'd want to do effectively is maybe run some quick checks. Sorry, these are just walking through what I just did. Do we have a functor? Well, like probably. If I define an arbitrary version of tree A, which is beyond the scope of this course, but I did it, I uploaded it. We could do a quick check. So here's a quick check. I'm saying I have a tree, map the identity to it. Is it a tree? It's like the same tree? Yep. Okay, so probably this passes the first functor law. We can quick check the second functor law, but this is a little bit, requires a little bit more of a nuanced quick check because you have to generate custom random functions, which has a special syntax here, which you're going to play with a little bit on your tutorial here. But this basically says, quick check my tree for this arbitrary function, like for this sort of arbitrary function and this arbitrary function, and check the second functor law. Right. So again, this is exactly why quick check was provisioned in Haskell, was in order to check these properties for functors. Something that's important here is we can't do quick checks on tree A. Right. The quick check can't choose can't just say, pick an arbitrary tree A for arbitrary A some kind. Right. It can only do it for concrete types, right? So we could test tree int, we could test tree bool, we could test tree string, but we can't test tree A. This was working over lists because technically lists are testing lists of tuples, right? And the Haskell community is kind of arguing about this, right? So for more on that, you can go to your tutorial this week. Okay, so how can I demonstrate that this tree functor satisfies the functor laws? Well, we do it in the same way. I'm not going to go through this proof line by line, just in the interest of time. We still need to get to applicatives, but I do want to highlight some important differences here because what's the minimum structure of this tree? Leaf. Is there more than one leaf? Yes. Was there more than one empty list? No. Okay, so it's not always the case that your minimum structure is exactly one thing. Here's an example where the minimum structure is a product type. It has many things. So it just takes a little bit of finagling on our proofs. Okay, so here's our proposition. Okay, given this information and the rules here that I've given you, right? That's the only thing that we can use. These assumptions and definitions and these line numbers. We then have to demonstrate maybe the second functor law. I think in class this week you're going to do the first one, the identity one. Right, so I'm just saying, okay, so my proposition is therefore P of T, right? T is some tree A. And I want to prove that if we map G.H to this tree, that is the same thing as mapping G, then mapping H to the tree. So here's the base case. So now the minimum structure of this tree A is a leaf, right? So I'm saying, okay, so I just have to check it for leaf of X. We don't have to do another induction here. Like induction is not always the tool. You can just say, look, X is arbitrary. It's not actually going to make any difference to this proof, right? So here I say, look, just consider T leaf of X, right? Unless X becomes like very important in the logical flow of this proof, it could remain arbitrary. Okay, so if we map G.H to leaf X, what are we going to get? Well, G.H is going to move inside the leaf container and become that. And we do that by line 3, applying F map H. Are we done yet? What else do we have to prove? How did we do this with lists? Like, remember the objective here. All right, we got to start. We have to say that if we map G.H, that's the same thing as first mapping H and then mapping G. Okay, so how can we start pulling out G and H's? Okay, I'm going to do one composition rule. Can we pull anything out yet? I highlighted G for a reason. Can we pull G out? What does that become? F map G over this leaf. Can we then pull H out? That's F map H over that leaf. If I use the composition rules, then I get that. Have we established it for this base case? Okay, cool. So therefore, P of leaf X, for any leaf X, that has type tree A, right? So that's the base case, just a little bit more complicated of a base case than we're used to. If we wanted to do this now for the general case, I'm just going to teach you how to set it up. You effectively say, okay, I need to now prove this is true for T, an arbitrary tree. But we know that arbitrary trees have this shape. So I'm saying let T equal node left tree, X right tree. That's the only way to build a tree. And I'm going to say, assume that this is already correct for its substructure. That is, I'm going to prove that the second functor law holds for this T, presuming that the second functor law holds for the left tree and for the right tree. Is it the case that the left tree and the right tree have to be smaller than T? Yes, because that's the substructure of the tree. Right, so this is how you set up your induction hypothesis. You're actually assuming two things, right? So if you work with any recursive data type, you just go ahead and you assume that that data type already satisfies the functor law for all of its substructure. And then using that information, if you can determine that it holds at the current level, then you've proved it. Okay, so I'm just going to go through this quickly. This one's free, right? The first one's usually free. There's like only one rule that really we can utilize here, and that is to actually map g.h into t, which gives you this. Does it? Oh, what did I do here? Oh, I'm just unwrapping t to what its definition is, and then I can go ahead and fmap g.h into there. So that's by definition. And then if I fmap that into here, it's going to map g.h to the left tree. That's what this one is. It's going to map g.h to the right tree. That's what this one is. And then it's going to apply g.h to the thing in the node. That's what we got here. And then we're just going to play the same game by rearranging stuff, right? Using the composition rules and then pulling things out, right? So did I highlight it? Yeah. So there's the thing we want to pull out is that fmap g. So that fmap g comes out of everything. Oh, did we use the induction hypothesis yet? Oh, that was the important part. Where was it? Right, because this is the statement of the induction hypothesis. I've made an assertion about the second functor law being true on the substructure. So we can already apply this, the second functor law there, and we can already apply the second functor law there, which is how I got this expression out of it. Okay, so moving on, we can identify that we sort of can unapply fmap g from that. We can identify, then we can unapply fmap h from that. And then we produce this after using some of our composition rules, which is the original statement. Once I take this and revert it back to t, the thing it was equal to by definition, and therefore pt. So therefore, we defined a new piece of data for tree. We defined a functor on it. Does it satisfy the second functor law? Okay, I'm going to tell you it satisfies the first functor law. You can give that some practice. And therefore, is this a functor? Yes, right? Provably so. Okay, yeah, right. It's coffee break, if anything. So that's the theory, but I just want to show you how to sort of utilize this in practice. So in the very first lecture, we were talking about the factorial function. And we were talking about the factorial function because we were pondering what factorial should do if I ever gave it x such that x was less than 0. Right? And we were discussing, like, should we ignore it? Should we let it run? And one of the things that I said was eventually we're going to have this maybe type. And last week we discussed how introducing this maybe type actually made everything really ugly because we had to like put things in containers and like remove them from containers. But let's see how we can treat this now. If I'm saying factorial is a function that maybe returns an integer and I give factorial x, x less than 0, what should this pattern be now that I have this maybe integer? Nothing. Perfect. Okay, that's the error type. What should factorial of 0 be? Just 1. Perfect. Okay, so this is the trouble now. What should factorial of x be? Well, I want to say that this is x times the factorial of x minus 1. Can I do that? No, because what type is this? What type is this? That's okay, so this basically could be like 4, and I want to multiply that by like just 3. Is there any way now that I can take that 4 and push it inside the container? How? Oh, well, yeah, you just want to sort of map that into there, right? To get just 4 times 3, right? So I can just now do that here. Did you say that's cool? Who said that's cool? Yes, it is cool. I think it's super cool. Right. So now I can have fact 4, fact 0, fact something we're not allowed. Okay. So this is why these functors and applicatives become necessary now, because we need to make our functions total. So we're always going to have things like maybe and things like either, but we don't want to like then have all of this complexity necessary from wrapping and unwrapping things. Right. So now you're able to like, now I've given you a tool where you can join the inside the box party. Right. But you have to leave the box eventually, and you can't change the outside of the box from inside of the box. That's the functor. Okay. But like, what about questions like this? If I want to do just 3 times just 4 or 5 to get just 15. Can we use the functor for that? No. So it's not good enough yet. Because it seems clear to me that doing something like this is something that I'd want to be able to do. And the answer to this is a Star Wars thing. Okay, because all right, so I can say just of the multiplication operator. I think I can do that. Starship operator, just 3. Starship operator, just 5. Okay, like this looks like a TIE fighter. That's why it's called the Starship operator. I'm not making this up, though I am tickled that it is called that for that reason, because I'm a huge Star Wars fan. Okay. So the next thing we want to do is figure out how to reconcile this problem. Like, I don't necessarily just want to jump inside the box. Maybe I want to take 2 things that are boxes and like apply some type of operation to them. So applicatives are going to solve this problem. Okay, so now that we have the generalization of the map routine, it becomes sort of like, that's our goal here. Generalize all the things. Why? I don't know. Just cause, right? We'll just generalize them all and see how far we can go until we like establish category theory. Bless you, by the way. Okay, so we can map +1 to like one. We can map univariate functions to objects. But like, what about like mapping bivariate functions to like 2 things? Like, wouldn't this be nice? I can say map plus to 1, 2, 3, 4, 5, 6 to get 5, 7, 9. Do we have something like this? Is there something that pre-exists in Haskell's system that is allowing me to do exactly this? It's not map. Yeah. Yeah, zip width, right? Like zip width exactly has this function type. But like maybe I don't want to stop there. Like maybe I want to take like something that's a trivariate function and give it like 3 things, right? So how can we solve this problem if I want to like introduce this to the system? Should I define map and then map 2 and map 3 and map k? Would it work? Well, it works for as many as you bothered defining. And funny enough, like this sort of is in the system because like tuples aren't a recursive type, right? They can't be. So we only have the number of tuples that like Haskell is like hard coded into the system. Yeah, I see people's eyes wide open, but yeah, you can't really have an infinite tuple. So this first one, like we can say, okay, fmap the successor operator to just 1 to get just 2. Maybe we can have fmap2 map that function to just 1 and just 2 to get that. And maybe we can have like an fmap3 operator that gives this trivariate function and add those things together. This approach is going to be insufficient. Why? We would have to hard code every fmap k into the system for like as large as a k as you bother. And there are an infinite number of these. So you better get typing now so you can finish before heat death of the universe in order to satisfy the theoretical requirement. Okay, so we're not going to do that. Instead, we're going to introduce the applicative class. And what the applicative class it's a different instance where you're going to get 2 extra functions, or you have to introduce the applicative, which gives you access to the Starship operator, where you have to minimally define these 2 functions to be part of the applicative class. You have to give me a pure function, and pure basically is an instruction about how to get into the structure. Right, we're talking about doing things over structure. Pure is like, okay, if I'm going to give you A and you put me in the box somehow. right? I don't care how you do it, but like if I give you A, you make that A part of the structure. It's sort of the most pure form of that structure. So if I give you one and one is to become a list, perhaps the most pure way of doing that is just to make the singleton list one, right? If I had a tree, which were never empty, that had leaves, perhaps the purest way of making one into a tree is to have leaf one, okay? And then you have to have the starship operator, which is give me structure over a function and structure over A, and I will give you structure over B. This is very similar to map, except now that you have your function is in the box. Okay, we already sort of saw that over here. Like I put a function into the box, and then I could starship operator with something in a box, with something else in a box to get the whole thing back. Okay. They also have laws that they have to satisfy. There are four laws here. If you put the identity function in the box and then you apply that, or I'm not sure what to call this, you applicatively apply it to X, then you should get X back. If you put G of X into pure, then you should get pure G, applicatively map that to pure X. If you get X, applicatively map that to pure Y, that's the same thing as taking pure. And okay, this is a little bit, this is a little, we have to parse this a bit because this is a little bit backwards than what we're used to. The input to your function here is fixed. You give me a function and I apply that fixed input to your function, right? So you give me G of function and I return to you back G, Y, and then you can regard this as $Y. And then the final applicative law here is just about how bracketing, sort of what the associativity property of the starship operator is. I'll talk to you about what sort of these mean, like Hutton gives some type of prescription in his book. It's hard to describe what these should mean because the true purpose of this is for sequencing things, which we're going to have to talk about later. This is for working with effectful actions. So the language and conceptualization of that's not going to become relevant until we start talking about the monad. Okay, so don't worry too much that these may not have sort of like really obvious meaning at the moment, but suffice to say, we're going to have to prove that anything we make an applicative satisfies those four laws. And they're going to give you one extra law called the coherence law. Don't Google this. This is something that's just intuitively clear, but I can't find any reference to it in the literature. Like, given that the functor laws exist and given that the applicative laws exist, this is a true statement. Right? Maybe we can try proving it, but we can just take it for granted. You can call it the coherence law. Pure G, starship operator X is the same thing as mapping G to X, right? So you see both. Right? You either see sort of some Haskell programmers prefer doing this, other ones prefer doing this. So that is to say, that statement there could have been written like this instead. Okay, I actually prefer the second one because you map that function to here to get a container with the function inside of it, right? So if we consider what's happening here, I don't have to do that. What this is going to do is sort of be equal to jest of 3 times. Right? And this is satisfies the typing information for an applicative, right? This is a box with the function in it, applying it to something else that's in the same type of box, right? So you end up going to get just 15 out of here, right? You should consider how this sort of evaluates, right? Because you evaluate that first to get a function in a container, then add that to get the final result. But if we did this for 3, you would keep generating functions that were inside of containers. Okay. Let's try to build the applicative for maybe, and then see how it works, because there's an important behavior here. So data for maybe A was what? You have nothing, and you have jest of A. So if we want an instance of applicative for maybe, where, okay, so now we need to define a starship operator and pure. Pure is easy. So give me A and give me something maybe A. And the starship operators give me a function that's in maybe, give me something maybe A, and give me back something maybe B. Okay, let's do this one. So, but how can I put pure A into a container? How can I get maybe A if I give you A? Just A. Okay. What about this one? So starship operator. I'm going to give you well, we have to, okay, remember, it's like one function for each of these types. Let's do the easy one first. If this is nothing, right? Is nothing part of this? Yeah, like maybe we have a function. Otherwise, you have nothing. So what does it mean to apply nothing to anything, you suppose? Nothing, right? There's nothing really else we can put. Was there anything else we could have put here? Can I construct something of maybe B with the information on the left-hand side of this equal? Nope. So our hand was forced. Okay. What about this one? I have maybe, oh, sorry, I have just something fabulous. Okay. And then I have just something that's A, or actually, I'll just say that this is maybe X, or so maybe A. That's the sort of naming convention for maybe types. You use this M in front of it. How can I get something over there that's maybe B? Yes, I have a function that takes something from A to B. I have something with maybe A. That just means, oh, go into the box party and apply this function there. What happens, but like what happens if this is nothing? That's handled by the functor. Okay, so usually you want to use your functor in your applicative for this reason. Okay, so let's try to, okay, so this is how the applicative for maybe is defined in the system. So let's just try asking ourselves some things. Okay, so I can say, so I should be able to have something like just plus one. Okay, so remember successor does that. It's just easier to bracket. Just successor, apply that to just one. What do you think we should get? I think this is okay. Just two. What about this? Well, this is equivalent to what? Remember that lawful. Okay, this is why I like thinking about it in the second way. So this was equal to pure this, right? Which I'm saying was equal to the map operator. So what should this equal? Nothing. What does it mean to map anything to nothing? You get nothing back. Okay. Will this work? Just the addition operator with just one and just two. What will this give back? Just plus one. And then can we apply that to just two to get what? Just three. Okay, but here's the thing that's important. What happens if I put a nothing here? Nothing. It propagates through that expression. What happens if I put a nothing here? Nothing. It propagates through that expression. That is to say, we have error handling now. Yeah. Why is it that what do you mean here? If I change that to there? So what's the type of MA? What's the type of FAB? Yeah. So this function, it goes from A to B. This is maybe A. I can't give a function that goes from A to B, maybe A. But I can push a function that goes from A to B into the box, where inside the box it has A, and then I can apply the function. So the answer to your original question is yes. That's why we had to use the functor, because of this typing compatibility. Okay, but the main thing we get from here is error handling, because it should be no surprise to you that this experiment is repeatable with this. Except now Okay. So we have error handling in the system now, and not in such a way where we have to do all this ugly putting things into boxes, taking them out of boxes, writing branches on those boxes. We just write expressions like this, and it doesn't matter if self-computations fail now. The applicative and functor is going to handle that for us, provided that, like, we've set them up reasonably here. Okay, so so all of the EdSTEM lessons I've given you for this week have error handling in them, like are basically using the either type or the maybe type. And you should be using this applicative and functor in order to do them. I think I gave you one question last week already. It was like RNA or something like this. Yeah, so you're going to do RNA 3 times. You did it last week when you didn't have this. Well, you shouldn't have used functors and applicatives. You should have suffered through that one. This week is going to get a little bit better because you have the functor and applicative. And next week, you're going to do it again when we introduce the monad. So like, I want that example is important because I want you to see it bloated and ugly, and then like sort of become nicer as we're introducing some of these higher features. Because like after we do the monad, like effectively no more Haskell features. It's just going to be utilizing these new tools to get print hello world, and then to do a bunch of parsing, right? I bought some party hats for that day. How many of you are here? I don't want it 3, 6, about 50. I'm gonna get 50 party hats, and we can wear party hats for a hello world party, and I'm gonna get a rousing standing ovation, right? Or I'll make the exam hard. Okay, so there's the maybe applicative, and this was the point, right? Now we have all of this error handling that's being handled by the system automatically. Right, so we talked about that. Okay, so I'm just going to tell you what Hutton said in his book. Like, don't worry about this too much because we don't really have a notion of what like an effectful programming is. But like, what these applications are typically used for is again when we start reintroducing some of these imperative notions back into our system, where we want to like accomplish a task 1 that can fail, then accomplish a task 2 that can fail, and accomplish a task 3 that can fail. And we're going to tie those things together using this applicative. So I'm just going to reiterate what Hutton says just for posterity, so you have it written in the slide so you can go back. Okay, so the applicative law 1 is mapping the identity function should have no effect, right? So applying identity should have no effect. Let's prove this for maybe. Should we be using induction here? Does maybe have infinite substructure? No. Okay, so that's the second lesson. Like, don't always reach for induction, right? Like I see that a lot in the exam where like people are just using induction because they think that's the thing that should be used, right? The structural induction is only useful when you have data types which have recursive data like substructure to them. Maybe is a product type. I know there's a lot of them, but it's effectively just 2 things. It's nothing and it's just something, right? And the A of the just A can be arbitrary. Okay. So let's prove this for maybe. So I need to prove that if we applicatively map this pure identity to X, that it's not going to change anything. And we're just going to do so by like rewriting things. So pure ID starship operator X is just ID starship operator X. So because pure in our setting was just putting the thing in the jest container. Okay, so we put the identity function in the jest container. Now what do we do? Well, our hand is forced, right? There's only one rule that we can use, and it's this one effectively. And that's to say, oh, well, this is effectively mapping the identity operator to X. What should we get if we map the identity operator to X? Why? Because it's a functor, and the first functor law says if you map the identity operator to something, you get the something back. So we get identity for functor rule 1. I don't think there should be an identity there. Well, anyways, you map identity to X to get identity X, and then you get X back. But I think I could have just written X there and invoked the first functor law to get that. Okay, so we've proved the first starship operator law or first applicative law for the maybe type. Okay, let's do the second one. So the conceptualization here is pure distributes over normal function application. That is, pure preserves function application. So that's what this means, right? Function application. Do I have a proof for this one? Okay, so here's how we can prove this one for maybe. Oh, did we have to do this for nothing? What, did I make any assumptions about X here? Nope. So we didn't actually have to do any case analysis because we never utilized the fact that X was a just or X was a nothing, right? That was all actually handled by this map operator. We may not get so lucky here. So let's see. As long as we're not exploiting the fact that X is either just or nothing, we're free to go. Okay, so let's see if we can prove this just by rewriting stuff. We want to rewrite from here to get to there. Okay, so what does it mean to have pure G applied to X? Well, just put it in the container. Is there anything here that seems obvious that we can do? Can we apply anything else? No, it seems that we're trapped. Can we unapply stuff? What do you think is sensible here to unapply? Yeah, take the G out. All right, G's inside the party, kick G out of the party. You're too drunk, G, get out of here. Okay, G, map to just X, we get that. Can we move from here to this form somehow? Remember this coherence law, right? This is equal, right? I said, what did I say? I said the coherence law states that pure X, this is equal to X map Y. That's always going to be true. Well, wrong way. Okay, so we get that. We take just back to pure, and that's the statement. This follows by rewrites, right? No case analysis required, no induction required. When an effectful function is applied to a pure argument, the order in which we evaluate the two components don't matter. This is what Hutton says in programming with Haskell. Look, I don't know. This is not how I conceptualize. There's an article I want you to read called The Problem with the Burrito Monad Tutorial. And the purpose of that article is that it's really hard to understand all of this stuff at a high level until you produce an analogy. But everyone sort of uniquely produces an analogy that works for them and then tries to explain to everyone else using that analogy where everyone needs like their sort of own individualized analogy. That's why if you search online, you're going to find a billion different analogies for how to understand the monad and the applicative. In fact, my inbox is replete with people sending me stuff saying, how come you didn't explain it this way? So that's why I want to have everyone read that article, because the article basically says the only way to develop your own analogy is to struggle with the high level stuff enough until some analogy materializes in your brain and makes sense for you, but then resist the urge to try and explain that to everyone else who's sort of on their own burrito journey. All right. So that being said, one of our tutors did write a pretty good explanation of her analogy from monad, which I'll post, but please don't savage me in the EdStem saying, if you'd only explained it by the burrito analogy, everyone in the class would have understood monads. This is kind of a personal journey. So this is kind of like Hutton's burrito. This is not how I understand the application. I like just trusting the types. Like, I don't know if I sort of got this from math where like, I'm okay working with abstractions. I'm like, yeah, it's fine. Like this is the applicative operator has this type. I can glue it to other things which types satisfy. That's sort of good enough for me, right? But if you read Hutton's book, he talks a lot about this in terms of these functions having effect on things. And for this one, it's just basically a statement about the order in which you do these effects sort of don't matter. In particular, it's this weird application here, right? So this is the weird lambda calculus expression where I give you you give me a function, I apply that function to fixed input. It's effectively equivalent to $y. But rather, let's just try to prove maybe actually satisfies this functor law. And now this sort of becomes, we now have to utilize case analysis on this, right? Because there's two patterns in maybe. So we have to sort of do the proof for just A and then do the proof again for nothing. So again, we're just going to go through these rewrites, right? So there's the initial statement. We eventually have to get to the target, which was what? We have X, starship operator applied to pure Y. We have to sort of, this has like, it's basically an expression of like the commutativity of this operator. You can switch the order of operations, but this has to actually switch as well, right? Inside here. So just write that down or keep that in mind. All right. So pure, of apply y to just 8. I think this time I'm actually starting on the right-hand side and going left, right? Because somehow that made more sense for this one. So how can we apply this to there? Well, I can drop that pure and I think change it with a map operation, right? Because that's the first coherence law. Then I can take this and map it inside jest to get that, right? Which is me giving the function to the input y, which means we switch around the dollar signs like that. I'm giving y to a, and then I can pull out a through that mapping operation, and then I can put the pure just container back on a and switch the map with an application, and then put the pure stuff back, and we get the thing as desired, right? Just through rewrites. We don't have to do some type of induction here. We have to repeat this for maybe, because here, like I started off with the just, right? So we were sort of assuming something with just. If I did this for nothing, this becomes easier because you just map to nothing, get nothing, and then you can unapply from nothing and go back. But it did require a case analysis. Okay. This one is, we're not going to go through it like totally carefully, but I just want to, the case analysis now can get a little bit tricky because there are three things in here, and those three things can either be nothing or just. And since there are three, do you think, how many proofs are we going to have to give here if we're going to exhaust all of the cases? Well, there's 2 options for X, 2 options for Y, 2 options for Z. Do you think we're going to give 8 proofs? No. There are only 2 proofs that sort of matter. If one of X, Y, and Z is nothing, that nothing is going to propagate everywhere. And the other proof is if none of them are nothing, right? So we're sort of adult mathematicians now. We can say that. We can say things like, I'm not going to give you 7 proofs for when one of these things are nothing because they're all going to look identical. I'm going to do it for one of them. And then I'm just going to say the other ones are the same as this with minor variations. Like I'm going to give you the power to sort of say that, right? If you're ever unclear, just ask us. I would never do something like this on an exam. Okay, so let's focus on the first one. We're all like, none of them are nothing. They're all sort of in the just container. And again, it's not induction here. We're just going to utilize rewrite rules. I'm going to go through this kind of quick so we can talk about using the applicative operator in a real example. But again, we're just replacing pure with its actual container in this case. Then I'm going to use the coherence law to change that to a map. Oh, actually, I just went ahead and did the map, it seems. Same thing's true for, okay, so rather than use a map here, we can just apply the starship operator properly. So if you see the starship operator and a container with a function in it and another container, that just means to push that into the container, which is what we did here. We're going to do that again with the jest B. I have jest, which is a container with a function in it, which I want to sort of apply to the thing inside this container, which gives you that. We can do it one more time, I guess. Yep. So I'm going to take this container with a function in it and apply that C to it, and we get that. I'm going to use composition laws to sort of change all the dollar signs. And now I can start unmapping these things, or not on. I'm doing the 2 things at once. I'm unmapping it and I'm using the jest. And then with the B, and then with the C, which means that we've actually shown this is true, right? This is sort of like the associativity property of these applied operations. Okay, so it's just rewriting here, right? And you can work. I'm sure I did this by like working down from here and working down from here, finding some common element, and then swapping. You got to get kind of good at like seeing when you can unmap stuff. That seems to be the secret sauce here. Okay, so again, the reason we're introducing these applicatives is because we get really desirable behavior when it comes to programming with errors or nothing types, right? So if I want to add 3 things together, I can add 3 things together. But if any of those things have nothing in them, you're going to push up that error through the ladder, right? Which this is going to be critical when we start doing parsing, because parsing can fail, right? But we're just going to write expressions for parsing that's like, you're fine. It can fail because all of the apparatus for sending those error messages through is already sorted. Okay. there are not many applicatives that actually exist on data types. That's why it's really hard to give new problems in this class, because there are not much data. And then when I give you data, there's like exactly one data type. Okay. For the for list, there are exactly two lawful applicatives that exist on lists, and I want to build it with you now because I insist that you know how Haskell's list applicative works, including for the exam, because it's important. Like list is like one of the most basic data types. You ought to know how the list type works. Okay, so we're just going to build it. I can't actually run it because I can't overload the data type, but we can do it like this. So data for list of A, this is either the empty list or A connected with list of A, something like this. Not sure that will actually run, but who cares? We have a functor on this. I'm sure we can all remember what the list functor works, but let's now do this. We want an instance for of an applicative for the list type where, and what do we need? We need two functions. We need pure, which given A gives you list A back, and we need starship operator, which given a list with a function in it and a list with A in it, gives you back a list with B in it. Okay, easy one. What should pure A be? List of A. Was there anything else we could have put here? Well, what about that? Probably won't be lawful if we're destroying information, right? So like when you're writing these things and information starts disappearing, you're probably like, that probably, if we're destroying input, it's going to be hard for that identity operator to do its thing properly if things are vanishing. But technically speaking, there are other type things we could have written here. Okay, so now we want to do starship operator. You have a function, you have a list of functions. So it's like FAB, fabs, or you have a fabulous function followed by a list of fabulous functions. And then you have something, a list of A's. How can we get a list of B's? B's. Right, so remember somehow like we want to be able to do something like this, like add 1, 2, 3 to 4, 5, 6 and get 5, 7, 9. Or at least this is one option here, right? Because one way of, it's hard to say this without giving the answer away, but okay. So this is the zip list. And actually it is one of the ways of defining a lawful list applicative in Haskell. This is not the way that it's done. So another way is, okay, I'm going to give you two lists and a bivariate function. How should we choose inputs to that bivariate function? So like this is the thing that should go in the first position of plus. This is the thing that should go in the last position of plus. Yeah, surely. But like, should we choose them like one by one? Well, that's the zipping with. Is there another alternative for doing it? Yeah. How about we just let all of them be inputs for all of them? Does that make sense? So it's like, what does it mean to add 1, 2, 3 to 4, 5, 6? Well, that means give plus any of these inputs as the first position and give plus any of these inputs for the second position. And that is going to be a lawful applicative. Right? 1, 4, 1, 5, 1, 6, 2, 5, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 9. So the way that the list applicative has been implemented in Haskell is to say, yeah, just let it up, like let the input, I'm going to give you a bunch of inputs to the function. The list applicative is going to say, choose as inputs all possible inputs from all of the things that you give me. And I'm going to return to you what the outcomes of those things are. Like strictly speaking, this was sort of Cartesian product. But that doesn't really tell the whole story, right? Because technically speaking, like, I could give a list of functions as a starting point here. Okay, so how do we actually implement that? All right, so we have a list of functions and a list of functions and a list of A's, and I want to get back something from B. So I'm going to say, take f of AB, give it A, such that f is drawn from FABs, and A is drawn from A's. Is that the right syntax, or am I programming in Python again? That looks right. Okay, I can't run this because I can't overload Haskell's list type. But that's how this is implemented, right? So if we do, I can just show you. Okay, so I'm going to build triplets. I'm going to map that to 1, 2, apply 3, 4, 5, apply 6, 7. Okay, and there you go. There's the Cartesian product of those things. Funny story. 3 years ago, one of the first questions I asked on A1 for this class was, write me a function that does the Cartesian product of these lists. And lo and behold, people gave me this as an answer. And I brought them into my office and said, this is amazing that you know how to use the applicative operator. Please use it to do this. And they all stared back at me and like, you guys cheated. So that was a fun year where I said, listen, like so many of you cheated that I don't actually want to like write this up because it's going to be such an admin burden. I'm going to reopen Gradescope. And if you like, you can re-upload a blank file for the thing that you may have included the Starship operator in. So that was a fun year. Okay, but anyways, this is how the list applicative works. You should know how it works for your exam. Always on the exam, I give some type of statement like this that has functors and applicatives in them, and I ask you to bracket it appropriately. And if you have a good working understanding of how the applicative should work, that shouldn't be too bad. Okay. So there's another way that we can do this using the zip with operator. So if this is how should we do this? If this was a list of functions, something that I could say this was zip with the application operator, those functions with that input. This would also be this would type properly, but then it wouldn't work because it wouldn't be lawful because of this. So something that you can go home and think about is how can you define, maybe we can do it now. Okay, we can do it. Okay, I have two options. Like we can work through the alternate for these for the list applicative, or we can use functor and applicatives on a exam style question, like a question I gave on the exam a couple years ago. Not all at once, guys. Like, let's raise our hand. Okay, you want the exam style one? All right. Maybe I'll put it on the homework. This zip list problem. Okay, so on the exam, okay, let me just go through these slides. Oh, wrong way. So I think basically that's just what I talked about. That's fine. Okay, so here's the exercise effectively. So just define a new type for lists. So since you cannot define another functor and applicative for lists, you can't overload the one that's there. So you have to create this new zip list type by just putting a dirty decorator over the list. But once you do that, then you should be able to define the functor and applicative, right? So I already gave you what the Starship operator should be. It should be zipping with apply the list of functions and the list, but you're going to have to give some thought about what should this pure operator be. So I think that's a good thing to think at home. I think on the exam, I had a function called map maybe, and it was something like I give you a function FAB, and I give you a list of maybe A's, and I wanted back a list of maybe. I wanted maybe a list of B. Now we should get pretty good at reading types. Like I gave usage on the exam, but like if I gave you a function that had this type, what would you expect it would do? Yeah, but like, can you give me some usage examples? So like the maybe came out, right? That was kind of the trick here. Yes, sir. Okay. If there's a nothing in here, return nothing. Otherwise, there's not a nothing in there. Everything there's maybe A. So you should be able to like put B's in this list and then give me back that thing. Now, how did I end up doing this? Okay, so let's see, because I may have used a do notation for this. So one of the reasons I gave this is because if you didn't use the applicative and functor, this became a disaster to try to execute on the exam. I'm not saying it's not possible to do it without those higher order types, but there was a lot of wrapping and unwrapping. People had to do all of the error handling manually. Okay, so let's do some of the free ones here. If I want to map maybe no function to the empty list, what do you suppose we should give back? Empty list, is that going to type properly? Okay, just empty list. Okay. Jeez, I didn't prepare for this, so hopefully this won't go too bad. Okay, map maybe, our fabulous function. And then we have maybe A with maybe A's. Okay, and what do I want to do here? Well, it's basically like just something. And it's just, and this is wish listing, right? Because I want to say, well, it's FAB applied to maybe A. And then I want to like connect this with map maybe FAB with the tail. Okay, but like how much of this isn't going to type? Like a lot of it, right? So first of all, what's the type of MA? Maybe. So can I put FAB over it? No. What can I do with it though? Okay, I can map it. Okay, so now this is going to be a what? That's going to be a maybe type. So it's either going to be nothing or it's going to be just something. Okay, so let's remember that. So that's either going to be just B or it's going to be nothing. How come I can't? There we go. What's going to be there? Well, what's this function returning? Maybe let's say this is either going to be just B's or nothing, right? Okay, so this is I can't cons that, but what can I cons? I have two things which may fail that are in containers. What operation do I want to apply to it? Like if everything was going fine here, all I wanted to do was say X con X is here, right? But I can't say just X cons just X's because they're in containers. Okay, so now I have to use like container arithmetic, right? Okay, so will container arithmetic work here? Just the cons operator. I think this will work. Hopefully this will work and I can let you guys go. Yes. Okay. Let's see. Map maybe +1 to just 1, just 2. Yes. What happens if I put a nothing in here? Okay. So for those who understood applicatives and functors, 2 lines. For those who didn't, impossible. Well, not impossible, but like a waste of like 10, 15 minutes. So this is just like an example of like on your exam, you have to think first. I know it's like really stressful to like not be writing on an exam, but you're not going to have to write much on my exam. Oh, and I gave 3 hours for the exam. Not to say that I've written a 3-hour test. I've tried to write a short test and if they would have let me give you 4 hours for the test, I would have given you 4. I'm just trying to alleviate the sort of time pressure. Okay, so a little bit of a heavy lecture will require a little bit of pondering, but give the exorcism a ponder. And next week, monads. All right, so double espressos next week. Okay, I'll see everyone next week, and then we'll get a break actually because of Labor Day. All right, bye, chat. I'll show the chat the merch. Where's chat? Here's the merch. If you want merch. It's for my wife. Well, I could put it on one of these days. Bye. Bye.